Hello, welcome to the second course in physics. I am Professor Sami Mahmood from Yarmouk University in Irbid, Jordan. This course will address a variety of topics starting with electrostatics, and then the field of electric currents and resistance will be addressed. After that, we will be discussing electric circuits, and then we will move on to the discussion of magnetostatics. Then after that, we will be talking about the time-dependent fields, electric and magnetic fields, and reach some relations between the electromagnetic phenomena. And after that, we will be talking about the alternating current circuits. Finally, the field of optics and optical instruments will be addressed. The objectives of this course will be concerned with, first of all, giving the students the knowledge, the basic concepts and fundamentals of electromagnetic phenomena, and enabling the student to be able to derive some mathematical relations related to the electromagnetic phenomena. The student going through this course should also be able to apply this knowledge that he gained to solve problems in electromagnetic theory. And finally, the student should be able to learn basic concepts and fundamentals of geometrical and physical optics, and should gain the ability to apply the knowledge in solving related topics and problems. The first topic which we'll be addressing in this lecture will be concerned with electrostatics. And within this topic, electrostatics, we'll be talking about a number of subtopics. The electric charge and force is one of these topics under the umbrella of electrostatics. The contents of this lecture will be as follows. First of all, we'll go through a quick introduction, and then we will be talking about electrostatic charges, the quantization of these charges, the conservation of these charges, and the distribution of charges in space. Then we will be discussing Coulomb's law, the force law between charges, and we will derive the inverse square law, which is the shape of Coulomb's law. So, in the beginning, as an introduction to the field, we begin by saying that anciently the Greeks have found that pieces of amber, when rubbed, they can attract pieces of straw. In a sense, the amber acquires some sort of ability to attract, to apply force on other objects upon being rubbed. The word electron, the name of this particle, the well-known particle in the atom now, is actually derived from the Greek word for amber. And this is the original observation for the electricity and the force of the electricity which is produced by amber being rubbed. The Greeks also found that some naturally occurring minerals and stones do have the ability to attract pieces of iron. And thus, the concept of force were there in both electrified objects, such as amber rubbed by a piece of cloth, and the forces are also existing in naturally occurring minerals and rocks. From these observations, the fields of electricity as a field of science and of magnetism have developed as two separate sciences, and this have gone for centuries. They were considered as two different fields. And as time goes, people started working on the electromagnetic phenomena and the relation between electricity and magnetism, and have found relations between these two classes of phenomena. In particular, in 1820, for example, Hans Christian Ørsted found that the passage of a current in a wire would deflect the needle of a compass, which introduces the concept that an electric current can lead to a magnetic force. And this has set the relation between the magnetic phenomena and the electrical phenomena. The electromagnetic theory was then, after that, developed by many scientists working in different parts of the world, in different countries. And the linkage between the two sets of phenomena has evolved as a consequence of these novel pieces of work. In particular, Michael Faraday, a gifted scientist, a truly gifted scientist, has done a lot of work on the connection between electric and magnetic phenomena. And he has done a lot and reached many very important conclusions without even using any mathematical equation. And that was a real genius. In the mid-19th century, James Clerk Maxwell has used the findings of Faraday and others. He has put Faraday's ideas into mathematical forms. He also introduced ideas of his own, like the idea of the displacement current. And these efforts have led to the evolution and development of the basis of the theory of electromagnetism. So this work is a collective work that was done by different scientists in different parts of the world, which moved the two sciences which were used to be thought as different from each other, electricity and magnetism, and we are reaching now a new era of these two parts as being two parts of one science, which is electromagnetism. Now let's talk about the electric charges in the beginning, and we start by saying that the electric charge is an intrinsic property of the fundamental particles that constitute matter, or from which matter is constituted. This is an intrinsic property just like mass and other intrinsic properties of matter. For example, what are the fundamental particles? Fundamental particles are like protons, for example, like neutrons in the nucleus. They are found in the nucleus. Like electrons going around in orbitals around the nucleus. Those fundamental particles, like protons, neutrons, and electrons, they have characteristic electrical property which is correlated with the concept of charge, electrical charge, that characterizes each one of these particles. So there is an elementary charge associated with the fundamental particles. I shouldn't say the elementary particles, because there are other particles which are more elementary than the protons and the neutrons. But for example, as the characteristics or features of these particles are as follows. The proton, designated by the symbol P, has a mass of 1.672 times 10 to the minus 27 kilograms, and the charge on the proton is 1.602 times 10 to the minus 19 coulomb. Coulomb is the unit of charge. Neutron N has a mass which is similar to that of the proton, 1.674 times 10 to the minus 27 kilograms, but it is not charged. It is neutral. The charge is 0 of the neutron. The electron, on the other hand, is much lighter than the previous two particles. It is 0.911 times 10 to the minus 30 kilograms in mass, and the charge is the same as that of the proton, but negative. It is negative 1.602 times 10 to the minus 19 coulomb. Thus, we notice that there is an elementary charge associated with these particles, and that elementary charge is E equals 1.602 times 10 to the minus 19 coulomb, and the fundamental particle could have that charge in positive or in negative, or it could have a 0 charge. The charge in a macroscopic world, in a macroscopic object, is the sum of these charges of all the fundamental particles from which of which the object consists. And because each object contains equal numbers of positive charges and negative charges, and we don't see any electrical phenomena associated with macroscopic objects, and the electrical effects are hidden because the objects are simply neutral. They contain equal amounts of negative and positive charges. The charge in nature is quantized. You cannot have any amount of charge you want. You can have amounts of charges that are simply a number, an integer multiplied by a quantity. Charge is discrete. It exists in quanta, in quantities. And the quantum of charge, the smallest known quantity of charge, is this E, which we have mentioned previously. And thus, experimentally it has been proven that the charge in an object is, as we just mentioned, an integer n multiplied by this smallest quantity of charge that is known. Also, there is another feature of charge, is that charge is conserved. You cannot create charge, you cannot annihilate charge. In the universe, charge is conserved. It has the same quantity. It does not increase, it does not decrease. Also, if we have an isolated object that means does not interact with the rest of the world, of the universe. An isolated object is also characterized by a conserved charge. Charges are not created or not annihilated within a macroscopic isolated object. So this is the concept of conservation of charge. And now we talking about the macroscopic objects, which are objects of a dimension. We can visualize that the charge is distributed over the objects in different forms. So, for example, charge can be distributed over a volume, and then we will have a volume distribution of charge. Charge can be distributed over a surface, or charge can be distributed along a line, and then we will have a linear charge distribution. These are the well-known charge distributions that we will be dealing with in our electricity problems to follow. The volume charge distribution, which is symbolized by rho, the symbol rho, is simply defined as the quantity of charge delta Q in a volume delta tau divided by the volume delta tau. So delta Q over delta tau will give you the volume density of charge in that volume, but that will be an average volume density because the volume delta T tau has some magnitude. However, if we take the limit as delta tau goes to 0, then in that limit, delta Q over delta T becomes dQ over dt. The volume d tau is approaching 0, and then the density is that we measure that way is the local density, rho at a point r, where the position r is the position of the volume element d tau. So that's how we define the volume density rho. Second, the surface density is defined in a similar way. The surface density sigma is defined as the limit as the surface area delta S goes to 0 of the charge delta Q on that surface element over delta S. So dQ by ds is simply the surface charge density at position r, and r is the position of the element ds, of the surface element ds. And the unit of this density is coulomb per meter square, because the area is meter square. And finally, the linear distribution is characterized by the linear density of charge. Lambda at position r is also defined as the limit of the charge delta Q in a length of that line delta L, as delta L goes to 0, which is equal to dQ by dL, and the unit is coulomb per meter. These are for the distributions and of charges. And now we move to talk about Coulomb's law. Coulomb's law is the force law that describes the force of interaction between two charged point objects. So if we imagine that we have a charged point object that is in the field of another point charge, Coulomb's law would give us both the magnitude and the direction of the force of interaction between these 2 point charges. The point charge Q1 and the point charge Q2 are separated by a distance r. These 2 point charges interact and they exert a force on one another, and the two forces of interaction are in the form of an action-reaction pair. And this, the forces are dependent on the type of the charge, of the charges that are interacting. So the forces of interaction could be either repulsive or attractive. For example, experience tells us that two positive charges separated by a distance r repel each other. So the force is repulsive between them. Two negative charges also repel each other. However, experience tells us that if one charge is positive and the other charge is negative, then the two charges attract each other. So the force between them is attractive rather than repulsive. The magnitude of that force of interaction is given by Coulomb's law, which reads: the force of interaction, the magnitude of the force of interaction between the two particles, point charges, is proportional to the charge of the first point, Q1. Also, it is proportional to the charge Q2. And it is inversely proportional to the square of the distance between them. That means it follows an inverse square law. And the constant of proportionality is K. Thus, this law, as we notice, it follows the inverse square law. And the proportionality constant that appeared in this inverse square law, K, is simply 1 over 4 pi epsilon naught, which is equal in magnitude 8.99 times 10 to the power 9 Newton meter squared per Coulomb squared. And here, epsilon naught is the permittivity of free space, which is simply equal to 8.85 times 10 to the minus 12 Coulomb square per Newton meter square. That is the permittivity of free space. Thus, we have a formula that gives us numerically the strength of the force of interaction between 2 point charges that is given by Coulomb's law. The direction of the forces between these two charges can be defined by the charges, the types of charges interacting, whether they are positive or negative, and using the fact that similar charges repel each other and dissimilar charges attract each other. Thus, for example, if we have two positive charges and we define the unit vector that points from charge Q1 towards charge Q2 if we define it as U1, U hat, then the force that charge Q2 exerts on charge Q1 is repulsive, and it's in a direction opposite to the unit vector U hat. Introducing the quantity of the magnitude of the force and the direction of the force, then F1, which is the force exerted on charge 1 by charge 2, is equal to minus Q1 Q2 over 4 pi epsilon naught R square U hat. Minus U hat is to show the direction of the force exerted on charge Q1. And now, if the charges have opposite signs, one of them is positive, one of them is negative, then the force exerted on charge Q1 is in the same direction as U hat, which means that the force F1 is directed towards the charge Q2, towards the charge which is interacting with it. So thus we realize that in the case of similar charges, the force exerted on one of them is away, directed away from the other charge. And in the case of dissimilar charges, the force exerted on one charge is points toward the second charge. This, in this case of dissimilar charges, the force exerted on charge Q1 is equal to plus Q1 Q2 over 4 pi epsilon naught R squared U hat, which indicates that this force is directed towards the opposite charge. And we must remember that according to Newtonian mechanics, the two forces exerted on charges Q1 and Q2 due to their interaction are equal in magnitude and opposite in sign, which means that F2 as a vector is equal to minus F1 as a vector, which means that the force exerted on the second point charge is equal and opposite to the force exerted on the first charge. This is a consequence of Newton's laws of mechanics. If we have n charges rather than two charges, then these n charges interact independently in pairs. And charge Q1, for example, if we have one of these charges, this charge experiences a total net force exerted on it, which is the sum of the individual forces acting on that charge by all other forces. And this is the so-called superposition principle. So the superposition principle states that in order to calculate the force exerted on one charge, we calculate the forces exerted on that charge by one charge and by another charge and by the third charge and add them up together, and the sum of these, of all of these charges, forces gives the total force exerted on charge 1, that is F1 equals F12, which means F acting on charge 1 due to charge 2, plus F13 due to charge 3, plus F14 due to charge 4, until we reach the force exerted on charge 1 by the nth charge. So this summation is a consequence of the superposition principle. And in order to write it in a general manner, suppose that we have a charge Q acted upon by a variety of charges, then the total force acting on charge Q is equal to the summation of the forces on charge Q due to charge Qi, and the summation runs over the index I from 1 to n. And in this formula, U sub I hat is the direction of the force acting on Q by the charge Q sub I. And as we mentioned just a little while ago, we mentioned that the force of interaction between 2-point charges is given by Coulomb's law, and Coulomb's law is an inverse square law, as we mentioned. The force, the magnitude of the force, is inversely proportional to the square of the distance between the 2-point charges. We must have in mind that the Coulomb's law of force applies to the force of interaction between 2-point charges only. We cannot apply Coulomb's law to an extended distribution of charge. In that case, we have to use calculus in order to calculate the total force exerted on a point by an object which has dimensions, which is not point-like. And coming up to this concept of the inverse square law, now we move to the derivation of this relation, which is the inverse square law. People working on electrical phenomena have reached several conclusions, and they have observed several phenomena. Some of them looked strange somehow. For example, Franklin noticed that if a charge is placed inside a metal vessel which is charged, then this charge inside the metallic charged shell will experience no force. So this was an important observation. Although this charge, if it exists outside the charged shell, it experiences a force. But if you put it inside the charged shell, it experiences no force. That was an important observation. And this observation was also confirmed by the scientist Priestley. Now, before that, in the 18th century, during Newton's time, Newton has demonstrated that if we have a shell of matter, that shell of matter exerts no gravitational force on a body that is placed inside that shell, only if the inverse square law is valid for the gravitational force. And since the matter shell was observed not to exert any force on a body that is placed inside it, then Newton concluded that the gravitational force must follow the inverse square law. So gravitational force accordingly was an inverse square law. That means the strength of the force goes as 1 over r square, where r is the distance between the two interacting objects. Priestley accordingly concluded that the same argument must be applicable to electrical phenomena. And he assumed accordingly that the same law must hold for the electrical forces, meaning the inverse square law. Cavendish independently have deduced the inverse square law for the electrical force by reasoning similar to that of Newton's. So now, if we follow that argument of Cavendish, we consider a point charge Q that is placed inside a hollow charged conducting sphere. So this is a conducting sphere that is charged and it's hollow, and the point charge Q is inside it. Now, if we draw a position vector from that charge Q to the surface, if we draw a straight line that intersects the spherical surface in 2 points on two opposite sides of the charge Q, and we take a small solid angle d omega that is subtended at the charge, at the point charge, that solid angle will cover a surface area, a small surface area, ds on either side. The surface element on one side is at a distance r1 from the point charge Q, and the surface element from the other side is at a distance r2 from the point charge Q. Now the solid angle d omega subtended by the surface elements is given by, from the first surface element, it's given by dA1 times cosine alpha over r1 squared, where alpha is the angle between the real surface element at the spherical shell and between the projection of that element of surface perpendicular to the line to the point charge Q. And that solid angle d omega, element of solid angle, is at the same time equal to, from the other side, from surface area ds2, it's equal to dA sub 2 cosine alpha over r2 squared. This is the solid angle as we calculate it from the two elements of surfaces on the shell in which the point charge is enclosed. And accordingly, we derive the formula dA1 over r1 squared is equal to dA2 over r2 squared, where dA1 and dA2 are the surface areas of the two elements on the opposite sides on the shell. And now this is coming from the geometrical argument, and now we go to calculate the force. The force on the point charge that is exerted by the two surface elements. So this point charge must be exerted upon by two forces, one from the first surface area dA1, the charge on the first surface area, and the other from the charge on the second surface area dA2. But we must notice that the force coming from dA1 is in opposite sign to the force coming from dA2. So we must calculate these two forces, and then we add up these two forces in order to get the result. Let's assume that we don't know the force law in the beginning. And since the force depends on the distance between the two interacting objects, let's assume that this force depends on 1 over r to some power n. We don't know it, and we have to evaluate this power n. In this case, the force due to the first surface charge is k, which is the proportionality constant we spoke about, times the point charge q times the charge on the surface area, which is sigma times dA1, over the distance r sub 1 to the power n. That's what we assume the force law to be dependent on. And similarly, the force acting on the point charge by surface area dA2 is equal to K times the charge Q times the charge on the surface, sigma dA2, divided by r sub 2 to the power n. These are the two forces acting on the point charge. And now, in order to calculate the total charge along this line that we have drawn, which intersects the surface area in the two surface elements, we add up these two, and we say, since the total force on the enclosed charge is 0, then when we add these two forces, we must reach a conclusion that F1 in magnitude is equal to F2 in magnitude, and they are opposite, of course, in direction. And thus, we conclude that dA sub 1 over R1 to the power n is equal to dA sub 2 over R sub 2 to the power n. This is the second formula that we arrive at from the force law. And until now, we remember that we don't know the force law. We are assuming that it is proportional to 1 over r to the power n. And we are after evaluating this power n. Now, from these two relations that we have derived, one from geometrical argument and the other one from the force law, we divide these two results, and we get 1 over r1 to the power n minus 2 is equal to 1 over r2 to the power n minus 2. And since in general r1 and r2 are variables, they can take any value, then 1 over r1 to some power cannot equal 1 over r2 to the same power for any values of r1 and r2. The only result, the only way that this result can hold valid for any value of r1 and for any value of r2, the only solution is that if we have n equals 2. In this case, n equals 2. In this case, the exponent of r1 is equal to 0, and the exponent of r2 is equal to 0. So we reach 1 over 1 is equal to 1 over 1, which is an identity. And this proves the inverse square law, 1 over r squared. And by this, I finish this lecture, and goodbye.